You ever notice something really strange? You can sit down with a pencil and paper, scribble some equations about how a ball should fall, and then actually throw the ball and watch it do exactly what your math predicted. That's weird, right? I mean really weird. The universe doesn't care about our equations. It doesn't read our textbooks. So why does it obey math? This question bothered one of the greatest physicists who ever lived, Richard Feynman. And the answer he arrived at is going to surprise you, because it's not what you think. It's deeper, stranger, and somehow more beautiful than just saying math is the language of nature. That's a bumper sticker. The real story is much more interesting. Let me start with something simple. Imagine you're a kid, maybe 5 years old, and you're playing with blocks. You stack 2 blocks, then add 3 more, and you count them. 1, 2, 3, 4, 5. Every single time you do this, you get 5 blocks. Not sometimes, not usually. Every time. You've just discovered that 2 plus 3 equals 5, and here's the thing. This isn't just true for blocks. It's true for apples, it's true for stars, it's true for anything you can count. The universe seems to respect this pattern we call addition. But why did you invent addition, or did you discover it? This is where things get interesting. You might say you discovered it because the pattern was already there in the universe. But then I could ask, was it really? What if addition is just a story we tell ourselves that happens to match what we see? What if the universe doesn't care about addition at all, and we're just really good at finding patterns? Let's go deeper. Think about throwing a ball. You throw it, it goes up, slows down, stops for a moment at the top, then comes back down. Now, way back in the day, someone like Galileo watched this and thought, I wonder if there's a pattern here. He measured how far the ball went at different times. He made tables of numbers. He noticed something beautiful. The distance the ball fell was proportional to the square of the time. If it fell for 1 second, it went a certain distance. If it fell for 2 seconds, it went 4 times as far. 3 seconds, 9 times as far. That's a mathematical pattern. But here's the question, did Galileo discover that the universe follows this mathematical pattern? Or did he invent a mathematical description that approximately matches what the universe does? See the difference? It's subtle, but it's everything. Let me try an analogy. Imagine you've never seen a cat, and someone hands you a photograph of a cat. You study this photograph really carefully. You measure everything. The length of the whiskers, the color of the fur, the shape of the ears. You write down all these measurements in a notebook. Now, have you discovered the cat, or have you created a description of the cat? Obviously, you've created a description. The photograph isn't the cat. Your notebook full of numbers isn't the cat. They're representations, they're models. Physics is kind of like that. When we write down equations describing gravity or electricity or quantum mechanics, we're not capturing the actual thing. We're writing down a description that matches our observations. The map is not the territory, as they say. The equation is not the universe. But here's where it gets really interesting. Our descriptions, our mathematical models, they work shockingly well. Way better than they have any right to. You can predict eclipses thousands of years in advance using math. You can calculate where a spacecraft needs to fire its thrusters to reach Mars. Do the calculation years in advance, and it works. The spacecraft gets there. That's absurd when you think about it. We're pushing symbols around on paper, following rules we made up, and somehow the universe cooperates. Einstein had a great quote about this. He said the most incomprehensible thing about the universe is that it's comprehensible. Why should we be able to understand it at all? We're just apes with slightly bigger brains stumbling around on a small planet. Why should the universe be written in a language we can decode? Here's one possible answer, and it's the one Feynman leaned toward. Maybe the universe doesn't actually obey math. Maybe math is just a really useful tool for making predictions, and we keep the math that works and throw away the math that doesn't. In other words, we're selecting the mathematics that fits, not discovering that mathematics is fundamental. Think about it like this. Imagine you're trying to describe the shape of a mountain. You could use geometry, measure angles and distances, create a mathematical model. And your model might be pretty good. You could use it to predict how long it takes to climb to the top, or where water will flow when it rains. But the mountain doesn't know about your geometry. The mountain just is. It's sitting there being a mountain, completely indifferent to your equations. The same might be true for the universe. When we say an electron has a certain charge or moves in a certain way, we're describing our observations using mathematical language. But the electron doesn't have charge in the way we think about it. Charge is a concept we invented to describe how electrons behave. The electron just does what it does. But wait, you might say, that can't be the whole story, because our math predicts things we've never seen before, and then we go look and find them. Like we used math to predict the existence of Neptune before anyone saw it. We used math to predict antimatter before we found it. How does that work if math is just a description? Good question, really good question. Here's the thing. When you build a mathematical model, you're building a machine for making predictions, and sometimes that machine spits out predictions you didn't expect. It's like writing a computer program to add numbers, and suddenly realizing the same program can multiply if you use it cleverly. The program doesn't know about multiplication. You built in addition, and multiplication emerged as a consequence. When physicists built up the mathematics of electromagnetism, all the equations describing how electric and magnetic fields work, they found something hiding in those equations. Waves. The math predicted that electromagnetic waves should exist and should travel at a specific speed. Someone did the calculation and realized, hey, that speed is the speed of light. Maybe light is an electromagnetic wave. And they were right, but the universe wasn't obeying the math. The math was capturing something real about how the universe behaves. And once you capture that behavior mathematically, you can explore the consequences of that behavior on paper. It's like having a really good map. If your map is accurate, you can use it to predict things about the territory you haven't visited yet. You can say, if I walk north from here for 3 miles, there should be a river, because that's what the map says. And if the map is good, there will be a river, but the river doesn't exist because of the map. The map is good because the river exists. So maybe the right way to think about it is this. The universe has regularities, patterns, things that happen the same way over and over. Drop a ball, it falls. Heat water, it boils. Charge flows from high voltage to low voltage. These regularities are just facts about how the universe is. Mathematics is a language we invented that turns out to be really good at describing regularities. When we say the universe obeys math, what we really mean is we've found mathematical descriptions that match the regularities we observe. But here's the mystery that still remains. Why are there regularities at all? Why isn't the universe just random chaos? Why does the same experiment give the same result every time? That's the deeper question. If you drop a ball today, it falls. If you drop it tomorrow, it falls. Why? What enforces that consistency? Some people say, well, that's just the laws of nature. But what are laws of nature? They're not like legal laws that you can break and get punished. They're descriptions of what always happens. Saying the universe has laws is just saying the universe is consistent. But why is it consistent? Here's where we're going to dip our toes into some really deep water. One possibility is that the universe is consistent because it has to be. Maybe inconsistency doesn't even make sense. Like, Can you imagine a universe where 2 plus 2 equals 4 on Monday, but 5 on Tuesday? What would that even mean? Maybe the very concept of existence requires some kind of logical structure, and that logical structure is what we recognize as mathematical. Another possibility is that we're fooling ourselves. Maybe the universe isn't as consistent as we think. Maybe we've just looked at a tiny slice of reality, the slice that happens to be consistent, and we're mistaking that for everything. It's like if you only look at calm days, you might think wind doesn't exist. We might be missing the chaos because we can only study the parts that have patterns. There's also a really wild idea called the anthropic principle. It says maybe there are lots of universes or lots of regions of one big universe with different laws, different regularities, different math. But we can only exist in a universe that has enough consistency for complex things like stars and planets and life to form. So, of course, we find ourselves in a universe that seems mathematical, because we couldn't exist in one that wasn't. It's selection bias on a cosmic scale. Feynman didn't particularly like the anthropic principle. He thought it was a cop-out, but he appreciated the mystery. He knew that just because we can describe something mathematically doesn't mean we understand why the universe is describable at all. Let me give you another angle on this. Think about symmetry. The universe seems to love symmetry. If you do an experiment today and get a result, and then do the same experiment tomorrow, you get the same result. That's time symmetry. If you do an experiment here and then do it over there, you get the same result. That's space symmetry. These symmetries aren't just aesthetic preferences. They have consequences, deep mathematical consequences. There's a theorem called Noether's theorem that says every symmetry corresponds to a conservation law. Time symmetry means energy is conserved. Space symmetry means momentum is conserved. Rotational symmetry means angular momentum is conserved. This is a profound connection between the structure of the universe and the mathematics we use to describe it. But again, we have to ask, is the universe symmetric because it obeys mathematical principles? Or do we describe it mathematically because we notice it's symmetric? The symmetry is real, it's out there in nature, but the mathematics is our tool for talking about it. Here's maybe the clearest way to think about all this. Imagine you're an alien who's never seen Earth. You're orbiting the planet in a spaceship, and you're trying to figure out what's down there. You notice patterns. You see green areas and blue areas and brown areas. You see white swirls that move around. You start building a model. You hypothesize that the blue stuff is liquid. The green stuff is some kind of growth. The white swirls are something else. You make predictions based on your model, and your predictions work. You can predict where the white swirls will be tomorrow. Now, is Earth obeying your model? Of course not. Earth is doing its thing. Water is being water. Plants are being plants. Clouds are being clouds. Your model is just a really good description. The better your model matches reality, the better your predictions. But the model isn't making Earth do anything. It's the other way around. Earth's behavior is constraining what models work. That's physics. That's the relationship between math and the universe. The universe does what it does. We observe patterns. We build mathematical models of those patterns. The models that match reality, we keep. The ones that don't, we discard. Over time, we get better and better models, and the better our models get, the more it seems like the universe is obeying math. But really, we're just getting better at describing what the universe does. Now, you might be disappointed by this answer. You might have wanted me to say something more mystical, like math is the hidden code of reality, or the universe is literally made of mathematics. Some physicists do think that. There's a guy named Max Tegmark who argues that the universe doesn't just obey math, it is math. That physical reality and mathematical reality are the same thing. It's an interesting idea, but it raises a question. Which math? There are lots of mathematical structures, lots of possible equations and systems and geometries. If the universe is math, which mathematical structure is it? And why that one and not some other one? You've just pushed the mystery back a level. Instead of asking why the universe obeys math, you're asking why the universe is this particular mathematical structure. Feynman's approach was more pragmatic. He'd say, look, I don't know why math works. Maybe nobody will ever know. But I do know that it works, and I can use it to figure out how the universe behaves. I can make predictions and test them. I can build technology based on those predictions. I can understand more and more about nature. And that's beautiful and worthwhile, even if the deepest why remains a mystery. And you know what? There's something profound in that humility, in admitting that we don't have all the answers, that the universe doesn't owe us an explanation. We're incredibly lucky that we can understand anything at all. We've got these brains that can spot patterns and build models and do math. And it turns out the universe is patterned enough that our models work. That's already miraculous. Demanding to know why it's miraculous might be asking too much. But let's not stop there. Let's push a little further, because there's something else weird going on. Not only does the universe seem mathematical, it seems to prefer certain kinds of math. Specifically, it seems to love elegant math, simple math, beautiful math. When physicists discover a new law, it's almost always expressible in a simple equation. Newton's law of gravity, Einstein's E equals mc squared, Maxwell's equations of electromagnetism, Schrödinger's equation in quantum mechanics. These aren't ugly, complicated formulas with hundreds of terms. They're short, they're elegant, they have a kind of aesthetic beauty. Why should the universe prefer simple equations? You could imagine a universe where the laws are incredibly messy and complicated, with dozens of special cases and arbitrary constants. But that's not what we find. We find simplicity hiding underneath complexity. There's a principle in science called Occam's razor. It says, given two explanations that fit the data equally well, prefer the simpler one. But why? Is simplicity more likely to be true? Or is it just easier for us to work with? Maybe both. Maybe the universe is simple, and our brains evolved to recognize simplicity, so we're particularly good at finding simple patterns. Or maybe, and this is a strange thought, maybe we only think the laws are simple because we've formulated them in just the right mathematical language. If you describe gravity using Newton's equations, it's simple. If you use Einstein's general relativity, it's more complicated, but also more accurate. And if you tried to describe general relativity in the language available to Newton, it would be insanely complicated. The simplicity depends on having the right mathematical tools. So when we discover that a law is simple, maybe what we've really discovered is the right way to think about it. We've found the mathematical language that makes the pattern obvious, and once you have the right language, everything becomes clearer. This happens in regular language too. Think about how hard it is to describe what you're feeling without the right words. You fumble around trying to express something and it's messy and complicated. Then someone teaches you a word like melancholy or nostalgia, and suddenly you can express the feeling simply. The feeling didn't change, you just found a better word for it. Math is like that, but for describing nature. When we find the right mathematical framework, the laws become simple. And the history of physics is partly the history of finding better and better mathematical languages. Newton used calculus, which he invented, to describe motion and gravity. Maxwell used vector calculus to describe electromagnetism. Einstein used differential geometry to describe spacetime. Physicists today use abstract algebra and topology and all kinds of sophisticated mathematics. Each new mathematical tool lets us see patterns we couldn't see before. So here's another way the universe obeys math. We keep inventing new math, often pure math with no practical application. Just people playing with abstract concepts. And then, sometimes decades or even centuries later, physicists discover that this abstract math is exactly what they need to describe some aspect of nature. It's like the universe was waiting for us to invent the right language. That's spooky, right? Mathematicians dream up imaginary number systems and strange geometries just for fun. And then physicists find those same structures hiding in the real world. Why? How does that happen? One answer is that mathematicians explore all possible logical structures, and physicists then search through that catalog to find the ones that match reality. There's a lot of math that doesn't describe the universe. We just don't hear about it because it's not useful for physics. So maybe it's not surprising that some math is useful. With enough math to choose from, something is bound to fit. But that doesn't quite capture how weird it is. Because the math that works for physics is often math that was developed with no thought of physics at all. It's not like mathematicians were trying to build tools for physicists and occasionally succeeded. They were following their own internal logic, their own sense of mathematical beauty, and the universe happened to match. It's almost like math and physics are exploring the same landscape from different directions. Mathematicians are mapping out the territory of all possible logical structures. Physicists are mapping out the territory of how nature behaves, and somehow the two maps overlap. The shapes mathematicians discover in the abstract, physicists find in the concrete. Maybe that tells us something deep. Maybe it means that the universe is constrained by logic, that there are only so many ways a consistent reality can work, and math is the study of consistency itself. So, of course, the universe matches math, because anything that exists has to be logically consistent, and math is the science of what's logically possible. Or maybe it's the other way around. Maybe our brains, our logic, our math, they all evolved in this universe. So they're shaped by the universe's structure. We think mathematically because we evolved in a mathematical environment. Our logic matches the universe because our logic is a product of the universe. In that case, asking why the universe obeys math is like asking why fish are so good at swimming. They evolved to fit their environment. There's probably some truth to both ideas. The universe has to be consistent, and our brains evolved to navigate that consistency. Math is the intersection of those two facts. But let's bring this back down to Earth. Or actually, let's go to Mars. When we send a spacecraft to Mars, we're betting everything on math. We calculate trajectories using Newton's laws and Einstein's corrections. We figure out exactly when to fire the rockets, how much fuel to burn, what angle to approach from, and it works. The spacecraft gets there, not approximately, exactly. That's trust. That's confidence that our mathematical descriptions match reality. Why are we so confident? Because we've tested it over and over and over. Every successful prediction strengthens our trust. Every satellite we launch, every bridge that doesn't fall down, every electronic device that works as designed. They're all evidence that our math is on the right track. But here's the thing, we're always ready to be wrong. That's the beauty of science. If we send a spacecraft to Mars and it doesn't arrive where we calculated, we don't say the universe broke the rules. We say our math was incomplete, we need better equations, and history is full of moments like that. Newton's laws worked great for centuries. Then we found situations where they didn't work. Very fast things, very heavy things. So Einstein came up with better equations, relativity, and those work even better. But even relativity isn't the final answer. It doesn't play nicely with quantum mechanics. So we know we need something deeper, a theory that combines both. We don't have it yet, but we're looking. That's the process. Observe, hypothesize, test, refine. Math is the tool we use at every step. It lets us be precise. It lets us make predictions that are specific enough to be wrong. And being wrong is how we learn. Feynman loved this about science. He loved that it was always provisional, always open to revision. He'd say, "I don't know if this is right. I just know it's the best we've got so far." That's honest. That's humble, and it's powerful, because it means we keep improving. So after all this, why does the universe obey math? Maybe the question itself is a little bit wrong. The universe doesn't obey math. Math isn't giving orders. Math is our tool for describing regularities we observe. The better our tool, the better our descriptions. The better our descriptions, the more it looks like the universe is following rules we can write down. The real mystery is why the universe is describable at all, why it has regularities, why the same causes lead to the same effects, why we can make predictions. That's the miracle, and honestly, nobody knows the answer. Maybe it's just how existence works. Maybe consistency is built into the very notion of reality. Or maybe we're incredibly lucky, living in a rare pocket of the cosmos that happens to be orderly enough for life and thought to arise. Either way, we're here. We can think, we can observe, we can build mathematical models that capture what we see. And we can use those models to understand more about the universe and our place in it. That's extraordinary. That's worth celebrating, and maybe, just maybe, the deepest answer is this. The universe doesn't care about our math. It's doing its own thing, following its own nature, whatever that is. But we care, we're curious, we want to understand. And we've discovered that this thing we invented, mathematics, this language of patterns and relationships, it's a key that unlocks doors. Not all the doors, not yet, but enough to see that there's something comprehensible out there, something we can grasp, at least a little bit. That's why we do science. That's why we keep asking questions. Not because the universe owes us answers, but because we've tasted the thrill of understanding, and we want more. We want to see what else is out there, what other patterns are waiting to be found, what other beautiful, simple, elegant truths are hiding in the complexity. And math is our flashlight in the dark. It doesn't create the path, it illuminates it. And every once in a while, we shine that light and see something nobody has ever seen before. A new connection, a new pattern, a new way of understanding how everything fits together. That's the real answer to why the universe obeys math. It doesn't. But we've found that math helps us see what the universe is doing. And that's enough. That's more than enough. It's everything.